All right, looks like we have the slides. I'm here to tell you today about my little piece of the water on the moon puzzle, which is the interaction of the water and the hydroxyl with the lunar regolith on a molecular level. So hopefully you've all seen the science papers in 2009. These have two testable results that they observed that we'd like to compare our results to. These are the variation with latitude, where there was more water seen at higher latitudes and thus probably colder temperatures, and then a variation with the mineralogy, or at least possibly with the mineralogy. There's a correlation between the Maria and less water signal on the moon. We're still working on getting actual lunar samples, so thus far we're using the micronized GHC1A. When I say micronized, I mean we actually put it in a micronizing mill and ran it for a while to break up the particles. The idea is to activate the surface a little bit and make it more like the actual lunar regolith. For the highlands, best sample we could get our hands on so far is micronized albites. A little bit about how we do the experiments. We do have an ultra-high vacuum chamber that we built specifically for these experiments. We have a base pressure in the -10 torr range, or 10 to the -10 torr. This is necessary to do these sorts of experiments. You can't even do them in the -9s. To introduce the water to the samples, we use effusive water dosing, which basically means we flood the chamber to -8 torr. And then we use liquid nitrogen for our cooling. This is sufficient for the majority of the lunar surface. One very unique thing we have in our chamber is a detachable cooling connection. This allows us to virtually eliminate all background signal, because when we get to the heating stage, we completely remove the cooling stage from the sample and we only heat the sample holder itself. So the actual experimental flow using this chamber is we cool first we deposit the powder, put it in full vacuum. Then we cool to a dosing temperature of 110 Kelvin in most cases. We expose the sample to the desired amount of water vapor. We then heat at a constant rate of temperature with time, monitor the water desorption with the quadrupole mass spectrometer, and record the quadrupole signal, which is the desorption rate versus temperature. Here I have some simulated data of just some very basic desorption curves, a zero at the first and a second order. I'll tell you what that means in a second. But from these curves, we do an analysis and we can get the desorption activation energy of the adsorbent from the material. We can also, in many cases, tell whether the water that we see desorb in the quadrupole started out as ice, molecularly chemisorbed water, which basically means that an individual water molecule finds a site on the surface that it binds to and sticks there with an energy higher than that of ice, so it'll come off at a higher temperature. And then hydroxyls will actually come off if you heat to high enough temperature, and they desorb as a second order process, where basically two hydroxyls have to become mobile on the surface, but they won't desorb until they find each other, react to form, in most cases, water, and then we see water desorption. The way we can tell these apart in the actual experiments is that the ice, as we increase the amount of water we expose the sample to, the ice will have its peak temperature move to higher temperature. The water, the molecularly chemisorbed water, will have its temperature remain the same, and then the hydroxyls that recombinatively desorb as water will actually move to a lower temperature as we increase the initial coverage on the surface. That will be important at the end of the talk. So now to our actual results. The first thing we did was to heat the sample to remove any water that was native to the sample already. We did this as a temperature program desorption experiment so we could monitor what came off. And we saw this peak that you see where, again, I've plotted the desorption rate of the water signal from the quadrupole versus temperature. And we have this peak centered at about 600 Kelvin. We were also watching the mass 2 for the hydrogen and saw a concurrent peak with this peak, with the 600 Kelvin peak. So we decided, well, this might be hydroxyls. The shape, we can't really do this experiment multiple times at different coverages to analyze the shape. So we're going to have to look at this a different way. So we actually quickly pulled pulled the powder out of the chamber, stuck it in Drift's infrared apparatus, and measured the difference between the signal near the 3 micron range from the annealed powder and ratioed that to a powder that we hadn't annealed. The red line is the difference between the two, and hopefully you can see hopefully you can see this, that it does not match water alone. There are there's these narrow peaks, and then there's shape over here that is indicative to us of hydroxyls having desorbed. So we think we've confirmed that this peak at 600 Kelvin is hydroxyls recombinatively desorbing as water. The desorption activation energy for these is about 1.5 to 2.1 electron volts. So we then expose the samples to these water doses these units are just a unit of exposure, and we didn't see any evidence of the hydroxyls coming back, which is consistent with the literature where you have to leave the samples out in the room for like a week or two before you see hydroxyls growing back in. But we do see other features from this narrow feature over at about 150 Kelvin, we believe is ice, water ice, of course. And then this feature over here could be one of two things. It could be ice that's bouncing around within our powder matrix and then trickling out over time, over a range of temperatures, or it could be a distribution of these molecular chemisorption sites. Looking at the inset at the bottom, we see that if we keep going to higher and higher exposures, that actually appears to saturate, which if we interpret this as being all chemisorption sites, we can get a value of 44 ppm of chemisorbed water, which will stick at temperatures that ice does not stick at. Similar analysis for the Highlands surrogate. We see a narrower, we still see ice, and then we see a narrower distribution of these, what I'm interpreting as chemisorption sites, which makes sense because the albite is a much less heterogeneous sample than the JSC1A. And then down at the inset again, we don't see any apparent saturation on the albite, even up to a much larger exposure than we used on the JSC1A. So we stopped the experiments at 512 Langmuir, and we just said, well, let's use this value as a lower limit. And that lower limit turns out to be 198 ppm of water, and those ppms are by mass. So I've been claiming that this is water chemisorption and not some sort of tortuosity problem, and this is the experiment we did that causes us to believe that is probably the case. If we look at the left graph, these temperatures up here represent the temperature at which I exposed the sample to the water. So if I dose the water at 200 Kelvin and then pump any remaining water out of the chamber, cool to 110, and then run the experiment just like I do in all the other cases, if this is just water bouncing around that had been ice originally, I would expect to see just a flat line of the baseline. But I do not see that. I see after the temperature that I do the water exposure at, the signal comes back. So we're currently interpreting this as molecular chemisorption and not some sort of tortuosity problem. Right, so then what I have plotted here is I took these temperature program desorption data for the saturating pressure or exposures, and I converted that to a concentration versus the desorption activation energy, at which the energy you have to give the water to desorb. And I plotted this cumulatively from highest energy to lowest energy. Okay, the data show that the albite is about 4 times more chemisorption sites than the JSC1A. And even if we try to normalize the surface areas to a common value, we still see that there are twice as many sites on the Highlands simulant as there are on the Lowlands simulant. So this is consistent with the spacecraft observations, at least in Science 2009, that showed more water or more 3 micron band depth on the Highlands than the Lowlands. If I take these concentrations from the previous graph and I run them through a lunar diurnal temperature cycle at a fixed latitude, assuming a solid sphere and lots of other assumptions that simplify it quite a bit, I get the data that's over here on the right, where I have the amount of water that survives for a given number of lunation, of diurnal cycles, where the temperatures are just the maximum temperature that the sample sees. So qualitatively, this agrees with the M-cube data, but we see about 100 times less than the numbers I've been able to find for the interpretation of the M-cube data. And in fact, if we extrapolate these data out to 50 million years, we see less than 1 ppm remaining even at 89 degrees latitude. So that suggests that a pulse of water early on will not stick around, at least not on the exposed surface. So some things that could help the water stick around are some sort of really slow diffusion process, which we don't see evidence in our experiments for this, but it doesn't mean it's not actually happening. We're continuing to look into that. It could be that these are surrogates and the lunar regolith will be more adsorptive, but I'm going to get the name wrong. I think it's Wallace et al. Recently published work that showed that, at least for chemical reactivity, the JSC1A is only 4 times less adsorptive or less active than the lunar regolith, not 100 times. So that doesn't seem like it alone can explain what we observe. Or it could mean there's a daily water source, replenishing the water on the surface. So let me quickly go through this. You may have seen this graph before. We've shown it a couple times, but it's a mechanism that our group is thinking about for water formation from the solar wind. Basically, the hydrogens from the solar wind come in, form hydroxyl groups on the surface. When the concentration builds up high enough, then, remember I said second order processes get, the coverage builds up, the activation energy or the temperature that happens at moves to lower temperature. So if you build up enough coverage, you can actually start having the recombinant desorption of the hydroxyls as water. And I've shown just some values that I tried out. This is from the initial heating recombinant desorption we observed. This is the middle of the peak, 400 Kelvin, and then this corresponds to about 1% of a monolayer of hydroxyls on the surface. And we see that a very, very simple calculation yields 10 to the 6 water molecules per second per centimeter squared of surface, which is about 1% of what I understand the flux of the solar wind is. But it's unclear whether this will all come off as water or whether we could get hydrogen instead. So that's a competing channel that we are looking into.
Okay. Thank you. Got time for questions? Dr. Elphick?
Solar wind protons come in with about a keV or so of energy, typically. They're coming in at 400 kilometers a second. So they actually don't like contact the surface of a grain and then hang out there. They're actually rocketing into the matrix. Right, going so hundreds of angstroms, if not 1,000
right,
angstroms.
So they'll implant at a depth that my colleague Jason McLean's poster has on it. Basically, we're looking into how likely it is for those hydroxyls to find their way to the surface and build up. But we do have geologic timescales to have it happen on, so it's worth looking into.
Okay.
So the water that's molecularly chemisorbed, like, can you describe a little bit how the water is actually bound to the surface, like what kind of site it would preferentially bind to? And
right. So any mineral has a lot of defect sites where you might have a missing oxygen from the lattice, or you might have like an extra oxygen on the surface. This creates a non-uniform potential where the water can come and actually form a weak chemical bond. Possibly filling this oxygen vacancy, for example.